Hello, Georgi Romanic here. Today I'm going to talk about the concept of scalar and vector variables. This is extremely important in physics, mathematics and natural sciences in general. This is atmospheric science channel and therefore these concepts are extremely important if we want to properly understand dynamics, thermodynamics, radiation and all other processes that are taking place in atmosphere, oceans, Earth, atmosphere system and so on. I already talked implicitly about many of these things in my previous video when I talk about wind. For example, wind is vector, temperature is scalar, but I never devoted one entire video to describe the fundamentals of these concepts. Today, I will fix that mistake. So at the end of this video, you will properly understand what is a scalar, what is vector, and as a bonus, I will provide you with a list of most common variables that we use in atmospheric sciences across the subfields of atmospheric sciences, and I will tell you which one are scalars and which one are vectors and give some additional discussion. That will also help you to see what is the future of this channel, how many different topics will be covered here, from cloud physics, radiation, dynamics of the atmosphere, which we are already covering, thermodynamics, and so on and so on. So let's see the difference between scalars and vectors. Scalar is a quantity that has only magnitude but no direction. If we measure temperature in this point, we say, for example, temperature is 5 degrees Celsius and there is nothing else we can say about temperature over here. We could say at some other point, for example here, temperature is 7 degrees Celsius, or temperature here 3 hours later is 2 degrees Celsius or something like that. But saying the number, the value of temperature, is everything. In other words, we cannot resolve temperature into components or some different constituent parts. Furthermore, any mathematical operation between two scalars is also a scalar. For example, a plus b will give result that is scalar. A times b, a divided by b, and so on. We will always get result that is a scalar. Scalars are also commutative, which means, for example, a plus b plus c is the same as a plus c plus b, and so on. Any combination of these three can work, and you can put brackets wherever you want, it's totally fine. Now, vectors are quantity that has three properties that describe it. Yes, three, not two, as you might have seen quite often somewhere else. And these three properties are intensity, or we also call it magnitude. 2 is orientation, and 3 is the sense. Now, in common day life, we quite often lump these two together and we say just direction. But you will see now that when we say direction, we implicitly describe both orientation and sense of a vector. First of all, let's see what is a vector. Vector is a pointing arrow. For example, this is vector A, let's say. That arrow has beginning, which we call tail of the vector, and end, which we call tip or head of the vector. Now, for this vector A, intensity or magnitude is the length of this arrow. Orientation is like a path on which this vector is positioned, and sense is showing us if the vector is pointing in this direction on the path, or it could be pointing in the opposite direction, let's say some vector m over here. Now vector m and vector A have the same orientation, they are on the same path, but they have opposite senses. This one has sense in this direction and this one in the opposite direction. Let me visualize this further using wind directions. If we are measuring wind over here, we say this would be northern wind, and here it would be southern wind. So let's call this one N and this one S. First of all, notice that I purposely increased velocity of southern wind and I indicated that by the longer arrow compared to wind that is coming from north. Now, notice that both of these winds have the same orientation. They are both in the north-south line of sight. However, they have opposite senses. And you can further understand this if you are talking to a person that is not very familiar with wind direction and meteorology, and you say, for example, tomorrow we have northern wind. That person would ask you, but does it mean that wind is blowing from north or towards the north? Because if you just said northern wind, it could be south or north. But by convention, we define northern wind as coming from north. So you can see in that definition, we include both orientation and sense, and we call that direction. But the sense is included when we say coming from north towards south for northern winds. I further implicitly talked about sense and orientation in my videos on centrifugal force and Coriolis force. In those videos I would say, we have X direction in the west-east line of sight, positive towards east. So you see, positive towards east, I included sense, orientation if I say just west-east line of sight. Change in a vector quantity can be change in magnitude, orientation, as well as sense. Also, in contrast to a scalar, vectors can be decomposed along different reference orientations. What do I mean by that? Let's say I introduce these two reference lines called coordinates. But now you see coordinates are nothing else but just reference orientations. And now we introduce sense to these coordinates such that this one is positive in this direction, this one is positive in that direction. And let's say I have vector A over here. I can decompose this vector along this reference line, which let's call X, and this one let's call Y, and I get that this is AX, component of vector A along the X direction, and here I can decompose it against the Y direction, and I get AY, which is Y component of this vector. This is something I cannot do for temperature. Let's say I have a temperature measurement over here, and it is, as we saw, 5 degrees Celsius. I cannot decompose this into anything. Now I would also like to mention a few other things. For example, can I say temperature plus wind? No, I cannot say that. Why? Well, first of all, I am summing up different units, and we know we cannot sum up different units. But even if the units are the same, I cannot sum scalar and a vector. Can I say temperature times wind? Yes. So scalar times vector is a possible combination, and the result will be something that is vector. Summing two or more vectors is a vector. For example, A plus B equals C, and this C is also a vector. A plus B plus C is the same as A plus C plus B. So summing vectors is also commutative. And I have a separate video describing how we actually sum up vectors and what does this operation mean. Can we multiply vectors the way we multiplied scalars? And the answer is yes, but it's more complicated because we have two different ways to multiply vectors. We have a dot b, and this is called dot product or scalar product because of this dot product, and the result is a scalar. But we also have cross product between two vectors, and the result is a vector. How to perform these operations is described in a separate video. Lastly, is it possible to create a vector from a scalar? And the answer is yes. And we do that using vector operators. And the most famous vector operator is del operator or nabla. Delta delta xi plus delta delta yj and plus delta delta zk, where I, j, and k are unit vectors. So if I apply this operator to a scalar, the scalar will be differentiated and then multiplied by this unit vector. What are unit vectors? We will learn in a separate video. But I hope that here you can see that the concept is basically the same as here. This is scalar. For example, if I apply this operator to temperature, delta T over delta X is some mathematical operation, derivative, but at the end of the day I get scalar, and then I multiply with this vector. Well, I multiply with this vector here, and it says yes, I can do that, and I can sum different vectors. Well, yeah, I can sum different vectors. So at the end of the day I will get a vector. Now also notice here that you can never say nabla or del operator dot t, because that would be dot product between vector and a scalar, and that is a no-no. You can say nabla t, that means nabla is acting on t. Can we say nabla dot v? Yes, we can, and this is actually called divergence. Can we say, for example, nabla cross v vector? Yes, we can, and that's called curl of this vector. Now, at the end, I made a list for you of common scalars and vectors that we use in atmospheric sciences. Temperature, dew point, which is also a temperature. Relative specific humidities, mixing ratio, all these are related to humidity. That's all scalars. Density, mass, salinity of water, pressure, viscosity coefficients, heat, entropy, cloud water content, cloud optical thickness, power spectral density when you start dealing with turbulence, wavelength, frequency, energy and work. CAPE is convective available potential energy, a quantity that we use quite often in atmospheric sciences, but you can see it's basically energy. Charge, voltage and current, electric flux, irradiance and radiance, albedo, visibility, precipitation amount, helicity, divergence. All these are scalars. And there are many more, I just included these. If you come up with some other one that is important and I missed, please let me know in the comment section below. Vectors are velocity, acceleration, angular velocity, force, vorticity, area vector of a surface, which is very important concept that shows the orientation of a surface, unit vector on a normal on a surface, gradients. Here we had a gradient, as you can see. Heat flux, diffusion flux, mass flux, electric and magnetic fields, Poynting vectors, and so on. Now I would like to point out something very interesting here. Flux of a scalar is actually vector. But if you have a vector and you flux it, and you calculate flux of a vector, you will get scalar. And this is something we will address in detail in a separate video. Something that not many people maybe know. So, looking at this, you can see if you study atmospheric sciences, you will deal with a lot of scalars and vectors, and there are many more. If you really love vectors, then you should study atmospheric dynamics, rotating fluid dynamics, and so on. If you hate vectors, then you should probably study thermodynamics, physics of clouds, and so on. Now, where you might go wrong, you might see here that you should study radiation if you don't like vectors, but you would be wrong, because irradiance and radiance are results or some of, for example, Poynting vector and some complicated vector interactions, and there is a lot of vectors and operations involving vectors when you study atmospheric radiation, as we will see on this channel later. Lastly, very lastly, notice that pressure is a scalar, but force is a vector. And we say that pressure is force over area. So how is this possible? If we divide vector by some number, area, we should get a vector, not scalar. But here is the trick. Pressure is component of the force normal to that area. And that's something that people usually omit. Now, when you say component of the force, then you extracted scalar from this vector, so you are dividing two scalars, and finally you get pressure that is scalar. Okay, I talked enough for this video. That was a very short overview of scalars and vectors in atmospheric sciences. So, welcome to diverse field of variables in atmospheric sciences. Until next video, goodbye.